Introduction. This material introduces the first steps in modeling a software system. Software development is made up of phases, which are often organized into cycles. The first of these phases is requirements specification. In this particular unit you will explore how to analyze the requirements document, the output from the requirements specification phase, to arrive at an understanding of how the proposed software system will be structured. Learning outcomes. After studying this unit you should be able to describe and use each of this unit's key terms summarized in the glossary section at the end. List the components that make up a conceptual model of a system domain, and describe briefly the form and purpose of each component. Explain why a conceptual model forms the basis for modeling the structure of the system, i.e., gives an initial structural model of the system. Use various techniques and guidelines to identify an appropriate set of classes and associations from a requirements document, including their attributes and multiplicities. Identify situations where a generalization relationship between classes exists, and decide on appropriate parent and child classes, and their attributes and associations. Use various criteria to decide whether an event should be modeled as a class or as an association. Identify invariants and express them in terms of classes, associations and attributes, and distinguish between valid and invalid combinations of objects and links. Identify and reason about derived attributes and associations. Draw simple object and class diagrams using the diagrammatic notations introduced in this unit. 1. Conceptualizing the system domain as classes. The first step in structuring the system is to model the system domain in terms of a collection of classes and the relationships between them. The system domain is the real-world context specific to the software system being developed. These classes are conceptual classes, not the software classes that will eventually form part of a working system. They are modeling elements corresponding to real-world entities mentioned in the requirements document. The relationships between them represent connections that are important in the system domain. The classes and relationships should all be ones that the client who has commissioned the software can easily relate to. You will see that, although building this initial model takes expertise, the result ought to be meaningful to someone who is non-technical but who knows about the system domain. So, for instance, if the requirement was for a system to administer a chain of shops, we might have classes such as, and so on, and relationships such as works at, and manages. This picture of the system domain as a collection of related conceptual classes will be referred to as the conceptual model. Once you have drawn up the conceptual model, you will use it as a basis for a series of models of the structure of the system, which will lead eventually to a specification of the software that is to be implemented. 1. 2. The aims of this unit. Starting with the requirements document for a hospital-based system dealing with teams of doctors, patients and wards, see the view document link at the foot of this page. The main aim of this unit is to construct a conceptual model for that system. In drawing up this model, the unit sets out some of the key activities and concepts that are involved in developing a conceptual model. Section 2 introduces techniques for analyzing the requirements document to identify conceptual classes and their attributes. Section 3 outlines the different types of relationships that can exist between classes and how to identify them. Sections 3 and 4 describes how the model can include other kinds of information which is discovered from analysis, such as events and constraints. Sections 5 and 6 shows you how to identify information that can be derived from other information in the model. Section 7, in the process of doing all the above, develops a conceptual model for the hospital system. Section 8 like class and object diagrams will be used to help you develop and think about the conceptual model. These diagrams can be used to describe the software classes and objects that will eventually be implemented in code, but they can equally well be used for conceptual models that deal with entities from the system domain. The UML is flexible enough for both purposes. Click the View Document link below to view the requirements document for the hospital system. You'll be provided with further links to this document as it's required. 1. 3. Studying this unit. This unit contains a number of self-assessment questions and activities, which are designed to reinforce your understanding of the concepts presented. These form an important part of the teaching strategy, and you should work through them as they arise, and read the solutions provided before moving on. This unit contains no practical exercises requiring the use of a computer. Some exercises will require you to produce diagrams. You could use a drawing package for this, or simply hand draw the diagrams. We expect you to spend about half your time on sections 3 and 4 of this unit, which cover the basic ideas involved in building a conceptual model. Sections 5, 6 and 7 are shorter, but cover concepts that you might find more challenging. The final section simply brings together the work you have done earlier in the unit. In studying this unit, you will need to refer to a PDF document containing information on the hospital system, which will be linked to within the text when required. Developing the conceptual model. 2. 1 Main activities in developing a conceptual model. In this section you will learn about the activities involved in developing a conceptual model, the role and purpose of the conceptual model, the position of the conceptual model in the wider context of the system that is being developed. The process of constructing a conceptual model starts with an analysis of the requirements document to identify those entities which are of key significance to the system, excluding any that are irrelevant or peripheral to its core functionality. In the case of the hospital system, for example, key entities will include things such as patients and wards. One category of entity that will be excluded at this stage is that which deals with details of input and output, the way in which information will be provided by and to human users of the systems. It is standard practice to separate the development of the user interface from that of the core system, and keep the two as independent of one another as possible. This is because it is quite likely that the user interface will need to be changed after the software has been delivered, for example to accommodate additional types of user or to take advantage of improved technology. This will be much easier to do if the user interface can be altered without requiring changes to the core system. Conversely, changes to the implementation of the core system should be possible while still keeping the user interface the same. Having identified entities that are of key significance to the system, we need to identify their properties and the various relationships between them. For example, patients are likely to have properties such as their name and age, and to be related to wards by virtue of the fact that each patient is on a particular ward. It is also necessary to identify constraints on the system domain i.e. limitations on the entities, their properties and relationships, and decide what conditions such constraints will impose on the model. The completed conceptual model will consist of a diagram representing the system domain, together with text describing important features of the model. In summary, the process which takes you from the requirements document to the conceptual model involves the following activities. Identification of those real-world entities described in the requirements document which are concerned with the core functionality of the system, leaving out considerations of the user interface. These will become the conceptual classes in the model. Identification of the properties of the entities and the relationships between the entities. Identification of the conditions that will be imposed on the model. Representation of the model using diagrams and associated text. 2. The role of the conceptual model. At the very heart of object-oriented programming is the philosophy that software objects can usefully correspond to real-world entities. This is why we create a conceptual model that looks object-oriented. It includes modeling elements referred to as classes, which have instances referred to as objects, and so on. Having a conceptual class such as shop, for example, makes it sensible to consider having a class as part of the software. Thus the conceptual model will provide an initial basis for the structure, or architecture, of the software, the classes and objects that make up the system and the way in which they fit together. That is, the conceptual model gives rise to an initial structural model for the system under development. It is important to recognize that whilst on paper the conceptual model and the initial structural model may look the same, they are not. They model different things, from different perspectives. A conceptual model is a representation of the system domain, whilst an initial structural model is a plan and early model of the software itself. The initial structural model does not deal with the behavior of the system, a way in which objects interact. Behavior is addressed by designing dynamic models, which you will study in later units. The way in which the conceptual and initial structural models fit into a full software development process is illustrated in Figure 1. Figure 1. The place of the conceptual and initial structural models in the software development process. The initial structural model is what is taken forward to the next stage of development. It will become the basis for designing the software system, and as you go along, many of the conceptual classes you identify initially will crystallize into corresponding software classes written in Java in this unit. But it is important to recognize that not all the conceptual classes will necessarily have software counterparts, and also that the software is likely to include classes which had no conceptual equivalent but which are needed in order to achieve a good software design. 2. 3. The conceptual model in the context of the wider system. The broad real-world context in which the software under development is to operate is known as the business area. This encompasses all the entities and processes, systems and subsystems that contribute to the activities of a business or other organization, as well as the communication between them. For example, the hospital system could be viewed as one subsystem in the general business area, which covers everything that goes on in hospitals. The dispensing of medicines, the training of nurses and doctors, and so on. Each of these activities may constitute a subsystem, which may or may not be computerized, but which will need to communicate with other subsystems in the broader area. The system domain is the particular subpart of a business area for which a software system is being developed. The entities in the system domain are those of potential significance for that system. For example, you know from the requirements document that the entities which form part of the system domain for the hospital system include doctors, patients and wards, but not nurses and medicines. Finally, that part of the software that is separate from the user interface and that contains objects corresponding to those in the system domain is referred to as the core system. In the real world, a system which dealt with the admission and treatment of patients might need to communicate with systems such as those controlling nursing shifts and the stock control of medicines. This unit will not be concerned with communication between separate systems. It will consider only the communication between the system and its human users, the staff who will be interacting with the system. Self-assessment question 1. A computer system is required for booking badminton and squash courts in a sports center which provides a number of other facilities for its members. A. Of what general business area might the system domain be a part? B. Suggest another system domain from the same business area for which a separate computer system might be needed. Answer. There is no single correct answer to these questions, and your solutions may be different from ours but equally valid. The system domain could be seen as belonging to the general business area of sports center management or administration. Alternatively, you could have seen it as belonging to a broader business area such as administration of leisure facilities. B. Taking the business area of sports center administration. Other required systems might include things such as a membership database, a staff records system, or a facilities maintenance system. In this section you have learned about what is involved in the process of creating a conceptual model and how this model forms the initial structural model for the eventual software system. You also learned about the conceptual model in the context of the wider system. Classes. 3. 1. Terminology and notation. In this section, you will learn ways of using a requirements document as a basis for identifying the conceptual classes needed to represent entities from the system domain. First, though, we will present some terms and notation associated with the process of analyzing the requirements document. Several of these will be familiar to you from your knowledge of software implementation, although here they will be used in a slightly different context to describe conceptual entities in the system domain. A class model is a category of real-world entities from the system domain. Although these may be tangible real-world things, they may also be intangible things such as events, roles and organizational units. Whether the entities are tangible or not, the modeling elements that represent them are referred to as objects. Objects of a particular class may have properties called attributes, corresponding to properties of their real-world equivalents. For example, an object representing a car entity may have an attribute that corresponds to the color property of a car. Note that, since objects of a particular class all have the same attributes, we also say that the class has those attributes. At any given time, an attribute of an object has a value. That is, specific information that the object holds in respect of that attribute. For example, the attribute of an object representing a particular car may have the value. Objects may also have links to one or more other objects, representing connections between real-world entities. If objects of one class can be linked to objects of another class, there is an association between the classes. Here is an example. Imagine a very simple system domain, where all we want to do is record information about a number of vehicles and their drivers, as follows. The number of wheels each vehicle has, and its color. The name of each driver. The driver who drives a particular vehicle or vehicles. In modeling this system domain there are two classes, and has two attributes, and has one attribute. If a particular driver drives a particular vehicle, the corresponding objects are linked. The classes and are associated because objects of the two classes may be linked. The UML provides notation for representing classes and associations using class diagrams, and objects and links using object diagrams. There they were being used to show software objects, in other words instances of software classes, but in this unit we will use them to represent entities in the system domain. The class diagram in Figure 2 shows the two classes and their respective attributes, any association between them, which we have called Figure 2, a class diagram. The inclusion of attribute names in the classes which make up a class diagram is optional. In this unit we will henceforth leave them out and instead, as you will see, include them in textual class descriptions. You might think that the name in Figure 2 implies that the association has a direction i.e., a driver drives a vehicle, but it does not. We could equally well have called the association instead i.e., a vehicle is driven by a driver. Figure 3 is an object diagram. It shows particular objects of the two classes shown in Figure 2 and the links between them that are instances of the association. Figure 3, an object diagram. In this example, an imaginary driver represented by an object identified as driver 4 drives vehicles represented by objects identified as vehicle 4 and vehicle 9. We have also invented some values for the attributes. It is often, but not always, the case that the attributes identified at this stage are later implemented as instance variables, but note that, at the conceptual modeling stage, no assumption is made as to whether attribute values will eventually be implemented in the software by strings, integers or any other type. Consequently, the value of the name attribute for the object driver 4 is not enclosed in quote marks as in Mr. Jones, since this would imply that it was to be implemented by a string. The links in Figure 3 are conceptual links, and at this stage no conclusions can be drawn about whether driver objects know about vehicle objects know about driver objects, or both these things. In fact, for all that is known, neither might apply. The conceptual links just mean that the real-world entities represented by the objects are related in some way. Only when deciding how the system will perform its tasks i.e., during dynamic modeling, will it be possible to consider how the software objects may need to interact. There is an important relationship between the kinds of diagram in Figures 2 and 3. The first, the class diagram, is general, and the second, the object diagram, is specific. A class diagram, as depicted in Figure 2, represents all the objects of the classes shown. Any association represents all the links between objects of the two classes. The object diagram in Figure 3 depicts particular objects and the particular links between them. When you go from the general to the specific like this, you refer to the specific cases as instances of the general category. Thus, an object is an instance of a class, and in exactly the same way a link is an instance of an association. This will sound very familiar from programming. After all, you already know that classes have instances, but remember that we are not talking about software yet. At the moment we are still discussing categories and entities from the system domain. The next subsection takes forward the idea of a class diagram. We begin by examining in more detail how to identify classes, attributes and associations from a requirements document. 3. 2. Identifying classes and attributes. The analysis process starts with the identification of a set of conceptual classes, the categories of things which are of significance in the system domain. There is not usually a single correct choice of classes to model a given system domain. Different people or different software development teams starting with the same requirements will not necessarily come up with the same set of conceptual classes. But good choices, those that accurately model the system domain, are crucial to the software development process. Inappropriately chosen classes may add complexity to later phases of the development cycle, and could make the software difficult to maintain or extend. When identifying appropriate classes, a good understanding of the system domain is important. The software developer often gains this through discussion with the client, assumed to be an expert in the area. Possible classes for inclusion may thus emerge during the course of the requirements specification process. You are in the rather artificial situation of having no client with whom to discuss the requirements. However, there are a number of other techniques that you can use to help identify appropriate classes from a requirements document. Textual analysis. Because a class is conceptually a set of objects of the same kind, and objects represent things in the system domain, nouns and noun phrases in the requirements document can be used as an aid to identifying possible classes. A noun phrase is a sequence of words like number of copies that functions as a noun and which can be used anywhere that a noun could be used. Below is an extract from the requirements document for a DVD library system with the nouns and noun phrases underlined. We have not included the acceptance tests, as these are derived from the use cases, so do not add anything to the description of the system. System domain. The DVD library holds DVDs of a number of films. It may have any number of copies of each film. The system should, for each film, hold the film's title. No two films have the same title. A library member can borrow any DVD of a film that is not currently on loan. However, no member can have more than 6 DVDs on loan at once. A borrowed DVD must be returned within 3 days. When a library member returns a DVD, it immediately becomes available for loan to other members. Each DVD has a unique identifying number. Each member of the library has a unique membership number. The system also holds each member's name. Use cases. The DVD library system will provide support to the library by enabling the library staff to do the following. A. Get number available. The staff member identifies the film. The system displays the number of copies available. B. List films. The staff member identifies the member. The system displays a list of the film titles and return dates for the DVDs that the member has on loan. C. Borrow DVD. The staff member identifies the DVD and the member who is borrowing it. The system records the fact that this copy of the film is no longer available for loan, the fact that it is on loan to the member identified, and the date on which it was borrowed. D. Return DVD. The staff member identifies the DVD. The system records the fact that this copy of the film is now available for loan and that it is no longer on loan to the member who returned it. Choosing the nouns and noun phrases is not an exact science. For example, in the second sentence of the above description, the object of the verb have is the noun phrase any number of copies of each film. Instead of underlining this phrase as a whole, we have chosen to identify number of copies and films separately within the phrase. In doing this, we are intuitively deciding that both copies and films are likely to be of importance. Another example is the noun loan, which could be treated as part of the phrases on loan to the member describing the status of a DVD rather than as a noun in its own right. This is only the first stage of identifying classes. We will shortly analyze the candidate classes in more detail. Some of the nouns and noun phrases underlined are duplicates, and some simply provide different ways of referring to the same thing. For For example, member and library member clearly refer to the same kind of entity as do title and film title. Such synonyms need to be grouped together to identify the distinct things that might help identify potential classes. A synonym for a word or phrase is another word or phrase that means the same as the first, and can be used in its place. On the other hand, the same word may be used to refer to different things. For example, number is used to refer to the unique identifying characteristic of both DVDs and members, as well as occurring in the phrases number of films and number of copies available. Activity 1. By grouping together nouns and noun phrases that are synonyms, list all the distinct entities that are mentioned in the requirements for the DVD library system. Discussion. Here is our list. Library also referred to as DVD library, DVD also referred to as copy, number of films, number of copies, film system also referred to as DVD library system, title also referred to as film title, member also referred to as library member, loan day identifying number, membership number, member's name, library staff also referred to as staff member, number of copies available, list, return date, fact date on which it was borrowed. There are a couple of things worth noting about this list. We have used a singular noun or noun phrase to represent each group of synonyms. This is a step towards assigning class names, which are always singular. In the system domain, DVD, a physical video disc, is synonymous with copy. The copies of the films are held on DVDs. In other contexts, copy might be synonymous with a recording on some other medium, e.g., a videotape or reel of celluloid. The DVDs or copies need to be distinguished from the films themselves, which are intangible. There may be many DVDs of a single film in the library. The solution to Activity 1 has advanced the process of identifying the classes needed to model the system domain. In other words, it has resulted in a list of candidate classes. For example, the second item in the list, DVD, suggests that all the DVDs in the library might be modeled by means of a DVD class. Every individual DVD entity would be modeled by an instance of this class. However, there clearly remains some weeding out to be done. Not all the items in the list will give rise to appropriate classes. Unfortunately, there is no mechanical technique for doing this. No set of criteria could adequately deal with the complexities and vagaries of natural language. Your ability to select appropriate classes will improve with experience, but below are some guidelines that should help you to narrow down an initial list. Guidelines for rejection of candidate classes. Though there are no hard and fast rules, your answers to the following questions should give you a strong indication of whether or not an entity really should be modeled using a class. Although, strictly speaking, it is the category of entity that is modeled by a class, we shall often use the word entity as if it were a category. Is it a property? Is it simply a property of some other type of entity in the system domain, or does it contribute to the system domain in its own right? If the former, it is likely to be appropriately modeled by an attribute of a class rather than a class itself. As you will see below, a good test of whether an entity should be modeled using a class or an attribute is whether it has or does not have properties itself. If it has properties, then it is likely to be appropriately modeled by a class. If not, then it is likely to be appropriately modeled by an attribute. Some examples of attributes from the DVD library are: title, an attribute of a film; identifying number, an attribute of a DVD; membership number, an attribute of a member; member's name, another attribute of a member; number of copies available, an attribute of film, but see further discussion below; return date, an attribute of a loan; date on which it was borrowed, an attribute of a loan. What about day? Number of days is also a property of a loan. However, as all loans are of the same duration, 3 days, there is no need to record this information for each loan. You will see later how this information is taken into account. Having decided above that number of copies available is to be modeled by an attribute of a film, should number of copies, that is, the total number of copies of a film, whether on loan or not, also be modeled by an attribute of a film? As you will see below, we believe that it is more appropriate to model number of copies in terms of links between films and DVDs. Does it refer to a behavior of the system? Does it name some process or result of a process that the system has to carry out? In the DVD library, a list of the film titles and return dates for each DVD is something that the system needs to produce as part of its behavior, rather than a category of entities that is significant for the system domain itself. Something else that could fit into this category is number of copies available. We have identified DVD copy as another candidate class, and the number of copies available is something that the system is required to produce. However, number of copies available can also be viewed as an attribute of a film, which is how we have chosen to model it. Is it outside the scope of the system? Is it a word or phrase that is used to help describe the general purpose of the system or what it consists of, but that does not actually refer to significant entities in the system domain? The library itself falls into this category. The system will operate in the context of the library, but will not need to represent the library per se. The significant entities are those with which the library is concerned, its members, DVDs, etc. You could think of the library as being the boundary of the system domain. Had the system been required to administer a group of libraries, then library might have given rise to a class, since it would probably be important to know, for example, which copy of a film was held at which library. Things such as user or, in the case of the DVD library staff, also fall into this category. Although they will use the system, they are outside its boundaries. In other words, the system does not need to refer to them. Does it refer to an aspect of the user interface? Does it concern the interaction of a user with the system, rather than something that is part of the system itself? There are no such examples in the DVD library system, since the requirements document does not provide details of the user interface. A more detailed requirements document might include statements such as the librarian enters the unique identifying number of the DVD using a barcode reader. In this case, barcode reader would be rejected as a class, since it refers to an aspect of the user interface. Does it refer to connections between other significant entities in the system domain? Such an entity might be more appropriately modeled by an association between two classes rather than a class. For example, it might appear at first sight that an entity alone in the DVD library system could be represented as a link between a member of the library and a DVD that they borrow. However, the DVD library system requirements indicate the need to record the date on which a device is borrowed, and to provide information on when DVDs are due for return. These dates are properties of a loan, so in this case we will model loans using a class, with the two dates as attributes. However, if the entity alone had not had properties, then it would have been more appropriate to model it as an association. Criteria for deciding whether an event, such as a loan, should be modeled as a class or an association will be discussed later in the unit. Is it a word or phrase that is used in talking about systems in general, rather than a reference to something in the system domain? Words such as system, behavior, and requirement fall into this category. They do not refer to entities in the system domain. Is it simply part of a language idiom? The requirements document may contain words which are just part of general English usage. For example, the system records the fact that this copy of the film is no longer available for loan could equally well have been written as the system records that this copy of the film i.e. excluding the phrase the fact, and the sentence the DVD library holds DVDs of a number of films would have meant exactly the same had the phrase a number of been omitted. A number of alternative solutions are possible when categorizing and selecting from potential classes. We might, for example, have categorized number of films available and list of titles and return dates as aspects of the user interface, as this is where they would be displayed. It may sometimes be the case that an entity in one of the above categories does need to be represented by a class in the core system, or that a decision is made to introduce a class not represented by a noun or noun phrase in the requirements document, or indeed not mentioned in the requirements at all. Furthermore, the same entity may perform more than one role. For example, if library members were able to use the system to reserve and check in DVDs themselves, library member would be similar to library staff in this context and so outside the system boundary, as well as being one of the entities being modeled. Having applied the guidelines to the entities identified in Activity 1, we are left with the following: DVD film member loan. All four of these represent significant entities in the system domain, and none of them duplicates any of the others. They therefore suggest categories of entity that can each be modeled by a different class. Notation for classes. For reasons of clarity, it will be useful to distinguish things in the real world, such as the list of categories produced above, from the conceptual classes and objects that will represent them in our model. To make this distinction clear, we will be showing, as above, categories of entity from the system domain in the same font as the rest of the text, and starting with the lowercase letter unless at the beginning of a sentence or, as in the case of DVD, where the entity name itself starts with an uppercase letter. However, the corresponding conceptual classes in the model and their attributes will be denoted in a different font e.g., DVD. It is important to realize that the classes being dealt with are conceptual classes and not software classes. Class names are always singular nouns, and each name should be a single word starting with an uppercase letter. The name chosen for a class should give some indication of the type of entity its instances are supposed to represent. Where more than one word is needed to achieve this, we will run the words together, capitalizing the first letter of each word e.g., Brickcode Reader. Applying these notational rules to the list of classes we have decided to include in our model for the DVD library system, we have DVD, film, member and loan. It is important to adhere to a set of agreed conventions for naming and capitalization. Kinds of class. The material below is adapted from Schleyer and Meller 1988, and Code and Jordan 1991. As a complement to textual analysis, attempts have been made to categorize likely classes by type. Aspects of a system domain that can be modeled appropriately as classes include tangible entities, roles, events, organizational units, abstract entities. Tangible entities are the physical things in the world of the system domain. Airplanes, vehicles, reactors, people and so on, i.e., things that can be seen or touched. Roles are played by people and other things in the system domain. Employee, student, lecturer, driver and so on. Roles differed from tangible entities in that a single person, a tangible entity, may have a number of different roles, e.g., parent, teacher, library member. Events. These include any significant circumstance, episode, interaction, happening or incident, e.g., deliveries, registrations, bookings, enrollments. We will discuss the modeling of events in more detail in Section 5. Organizational units. These include any parts of organizational structures to which people or things in the system domain belong: departments, faculties, branches, regions and so on. Abstract entities. These are things such as plays, novels, pieces of music, theories and political movements. They have an existence but do not correspond to tangible entities. For example, the play Hamlet is an abstract entity, while the books which contain the play are tangible entities. While consideration of categories such as the above can be useful, you should always remember that the overall purpose is to identify all the classes needed to model significant aspects of the system domain. There will sometimes be classes that do not fit neatly into any of the above categories. Activity 2. Consider each of our classes for the DVD library system in terms of the categories above. For each class, decide whether the entities it models fit into one of the 5 categories, and if so, which one. Discussion. The candidate classes can be categorized as follows: DVD tangible entity, member role, film abstract entity, loan event. Identifying attributes for the classes in the DVD library system. As a byproduct of our class rejection process, we have already identified a number of entities that can appropriately be modeled as attributes. A similar font and naming convention to that for classes will be applied to attributes, except that their names will start with a lowercase letter. Attributes of film. Title, number available attribute of DVD. Number attributes of member. Number, name attributes of loan. Return date, issue date. To check whether there are any others, it is necessary to read through the requirements document to ensure that no information about the properties of classes has been missed. In fact, none of the classes that we have identified has any additional attributes. For a simple system, it is often possible to identify attributes in parallel with classes, particularly when all the references to attributes are nouns. But suppose a requirements document contains something like the following. Each warehouse contains a number of barcoded products. Here, the term barcoded, although it is an adjective and not a noun, points to the need for a barcode attribute on the product class. Unless the noun barcode appeared elsewhere in the description, this could well have been missed during the class identification process. 3. Identifying classes and attributes for the hospital system. Identifying the classes for the hospital system. Now that you have been armed with a number of techniques for identifying appropriate classes for a conceptual model, you can apply them to the requirements document for the hospital system. The requirements document for the hospital system is set out in the PDF document below. You will need this in order to complete Activity 3. Click the View Document link below to view the hospital requirements. Activity 3. Use the textual analysis technique described earlier in this section to identify the nouns and noun phrases in the first part of the document, headed System Domain, and then eliminate any duplicates or synonyms so as to produce a partial list of entities in the system domain. To identify all the relevant entities, you would also need to analyze a section of the document entitled Use Cases, but you are only required to carry out part of the process. Discussion. Figure 4 contains the description with the nouns and noun phrases underlined. Figure 4. Identifying nouns and noun phrases. This is not an exact science, so do not worry if your underlining does not exactly match ours. After eliminating duplicates, we are left with the following list of entities. Synonyms are shown in parentheses. Hospital number of wards, patient type of ward, male ward, female ward, ward sex, capacity, maximum number of patients, number of beds, name of ward, administration department, information, doctor, team code, orthopedics, pediatrics, grade 1, consultant junior doctor, record of teams and doctors, care, number of doctors, number of patients. Your list may not have been identical to ours, but we would expect you to have included most of the entities above. Applying the guidelines for rejection to our solution to Activity 3, the following can be eliminated. Hospital and administration department outside the scope of the system. Number of wards, language, idiom. The requirements document could equally well have referred to wards or some wards. Type, capacity, name, attributes of ward. Sex, attribute of patient. Information, generic term referring to the behavior of the system. Team code, attribute of team. Record of teams and doctors, part of the behavior required of the system. Number of doctors, number of patients, language, idiom. You may have noticed that there are 3 nouns, orthopedics, pediatrics, and grade 1, which have not been eliminated using the guidelines for rejection, yet which common sense suggests should not be modeled by classes. Orthopedics A and pediatrics are in fact given in the requirements document as example values of team code, which was identified above as an attribute of team, and grade 1 as a value of an attribute, grade, of junior doctor. The grade attribute will be identified in Activity 4 below. This leaves, so far, the following list of entities which give rise to candidate classes. Male ward, female ward, ward patient, doctor, team, consultant, doctor, junior doctor, care. Identifying additional classes from the use cases. To finalize the above list, it is necessary to analyze a section of the requirements document dealing with the use cases of the system, and to apply the same guidelines and criteria for rejection. This may identify the need for additional classes, or it may provide information that enables us to eliminate more classes from our existing list. Having underlined all the nouns and noun phrases in the use cases section of the requirements document, eliminated classes already identified, and applied the rejection guidelines, we believe there are no additional classes. You may want to convince yourself of this by reading carefully through the use cases section. However, in our view, analyzing the use cases section of the requirements document allows us to replace 2 of the candidate classes by a single class, and reject 1 further class. Male and female wards. We initially retained these as potentially giving rise to separate classes because we could not be sure that the two types of ward played a similar role in the system. However, the use cases section of the requirements document makes clear that the two types of ward differ only in the sex of the patients that can be allocated to them. These classes can therefore be rejected in favor of a single class modeling wards with an attribute to denote the sex of the patients on the ward. Note that in the similar case of junior doctor and consultant doctor, both classes are retained because there are differences in the role that each plays in the system domain. Care. The care of a patient, as described in the requirements document, is significant only in respect of which team provides that care. The description identifies no specific functionality or attributes with respect to the care itself. We conclude that at this point there is no need for a class modeling care, and that the care of a patient by a team can be modeled as a link between the relevant patient and team objects. This leaves the following list of conceptual classes: ward, patient, doctor, team, consultant, doctor, junior doctor. Notice that these classes, now accepted as conceptual classes, are in the special font for representing conceptual classes. Identifying attributes for the classes in the hospital system. The next task is to identify the attributes of the conceptual classes listed above. We have already identified some of these as a byproduct of the process of identifying the classes. Activity 4. By referring to the system domain and use cases sections of the requirements document, suggest attributes for each of the classes in the hospital system. Discussion. For each of our chosen classes, here are our lists of attributes, together with references to the relevant parts of the requirements document. Ward. Name, type, capacity, number of free beds, system domain, use cases A, D, F. Patient. Name, sex, date of birth, age, system domain, use cases A, F. Doctor. Name, system domain, use case G. Team. Team code, system domain, use case G. Junior doctor. Name, grade, use case G. Consultant doctor. Name, use case G. Having identified a complete set of classes and attributes, they should be described formally, accompanied by short comments, as follows. Such class descriptions form an important part of the conceptual model. Class ward, a ward in the hospital. Attributes. Name, the unique name of the ward. Type, whether the ward is for male or female M or F patients. Capacity, the maximum number of patients that can be on the ward at any one time. Number of free beds, the number of free beds on the ward. Class, patient, a patient in the hospital. Attributes. Name, the name of the patient. Sex, the sex M or F of the patient. Date of birth, the date of birth of the patient. Age, the age of the patient in years. Class, team, a team of doctors. Attributes. Code, the unique code of the team. Class, doctor, a doctor at the hospital. Attributes. Name. The name of a doctor. Class, junior doctor, a junior doctor at the hospital. Attributes. Name, the name of the junior doctor. Grade, a grade 1, 2 or 3 of the junior doctor. Class, consultant doctor, a consultant doctor at the hospital. Attributes. Name, the name of the consultant doctor. 3. 4. Generalization relationships. We have already discussed links between particular entities in the system domain, and briefly introduced the concept of an association between two classes, a relationship whereby the instances of those classes might be linked in a way that is significant for the system domain. Self-assessment question 2. Suggest a possible association between any two of the classes team, consultant and patient, and give it a suitable name. Answer. You might have suggested any of the following, possibly with slightly different names. Cares for or is cared for between the classes team and patient. Is head by or heads between the classes team and consultant doctor. Is responsible for or is responsibility of between the classes consultant doctor and patient. Note that associations are highlighted by use of the same font that is used for classes and attributes. We will discuss associations in detail in section 4 of this unit, but there is another, quite different, way in which classes can be related. In the context of the hospital system, the classes junior doctor and consultant doctor are each related to the class doctor by virtue of the fact that all junior doctors and all consultant doctors are also doctors. This is referred to as a generalization relationship between the classes doctor and junior doctor, and also between doctor and consultant doctor. That is, the class doctor generalizes each of the classes junior doctor and consultant doctor. To put it another way, each of the classes junior doctor and consultant doctor is a specialization of the class doctor. That is, each of the classes junior doctor and consultant doctor specializes doctor. The doctor class is referred to as the parent class or superclass of junior doctor and consultant doctor, with the latter two classes being called child classes or subclasses of doctor. You saw earlier in the unit that a conceptual class is represented in a class diagram by a rectangle containing the name of the class and optionally the names of its attributes. Figure 5 shows two ways of representing generalization relationships in a class diagram. Figure 5, depicting the generalization of junior doctor and consultant doctor by doctor. Either style of diagram is equally acceptable. In your own work you should produce whichever style is easier for you. Note that the arrowhead points to the more general class. The orientation of the diagram is not significant. There is no need for a child class to appear beneath its parent class in the class diagram, although it frequently does so in practice. The implication of specialization is that a specialist class has its attributes and associations defined in two ways. Those that are common to all the objects of the more general class, and those that are specific to itself. When we identified attributes for the classes in the hospital system in Activity 4, we decided that all three of the classes representing doctors would require a name attribute. In view of what we have just said, that a specialist class has all the attributes of its parent class, this attribute can be removed from a junior doctor and consultant doctor classes, provided it is made clear in the model that both junior doctor and consultant doctor specialist doctor. In object-oriented parlance, the child classes in a generalization relationship are said to inherit properties from the parent class. So junior doctor objects, for example, will have a name attribute inherited from doctor, as well as a grade attribute, which is specific to the junior doctor class. You will see later that the class doctor has an association with the class patient representing the treatment by doctors of patients. Junior doctor and consultant doctor will also inherit this association. This is appropriate since, for example, the list patient's treatment use case for the hospital system specifies that the system must be able to list the names of doctors who have treated a patient. It does not specify a particular kind of doctor. Those listed may well include both junior doctors and a consultant doctor. This relationship between doctors and patients really means that there may be links between junior doctors and patients, and between consultant doctors and patients. In deciding whether a generalization relationship is appropriate, it is necessary to consider the kind of entity each class is modeling as well as any common properties and relationships. For example, a ward has a name, but a ward is clearly not a kind of doctor. An appropriate generalization relationship is one in which it is possible to use a real-world entity represented by an instance of the child class in place of a real-world entity represented by an object of its parent class. This property, in which an instance of one class can be substituted for an instance of another, is known as substitutability. Thus, in the statement each doctor is in exactly one team, junior doctor can be substituted for doctor. It is important to recognize that identifying a generalization relationship at the conceptual level i.e. in the conceptual model does not necessarily mean that the developers are committed to creating a similar inheritance hierarchy at implementation. Here are the modified class descriptions for the doctor class and its subclasses. Note the inclusion of comments to indicate the generalization relationship. Class Doctor A doctor at the hospital. Generalizes junior doctor and consultant doctor. Attributes. Name the name of the doctor. Class. Junior doctor. A junior doctor at the hospital. Specializes doctor. Attributes. Grade the grade 1, 2 or 3 of the junior doctor class. Consultant doctor A consultant doctor at the hospital. Specializes doctor. Attributes. None. 3. 5 Abstract classes. Activity 5. Read the following extract from the requirements for the hospital system. Each team is headed by a consultant doctor who is the only consultant doctor in the team. The rest of the team are all junior doctors, at least one of whom must be at grade 1. Each doctor is in exactly one team. What can you infer from this extract about doctor objects? Discussion. Because every doctor is in a team, and the only doctors in a team apart from the consultant are junior doctors, you can infer that each doctor object is in fact an instance of either consultant doctor or junior doctor. In effect, there are no doctor objects as such. A class whose instances are all actually instances of one of its subclasses is called an abstract class. The word abstract is commonly used to refer to something which is intangible or not concrete. You may already have met the concept of an abstract software class in your study of object-oriented programming. Java does not allow you to create any instances of abstract classes, since every instance of the abstract class is actually an instance of one of its subclasses. Do not confuse an abstract class with a class representing abstract entities, which you met at the end of subsection 3. 2. An abstract class is a class which conceptually has no instances of its own, but only instances of its subclasses. A class representing abstract entities may have instances, but instances which represent intangible entities like novels. In this unit we denote an abstract class in a class diagram by adding to the box representing the class, as shown in Figure 6. The notation in the UML is known as a stereotype, which is a label giving additional information about some component of a model. Figure 6. An abstract class with two subclasses. By no means all parent classes are abstract. If a class is not shown as, it is assumed to be a concrete class, i.e., it is intended that the class may have instances that are not instances of any of its subclasses. Activity 6. Consider the 3 following excerpts from requirements documents. In each case decide whether any classes appear to be involved in a generalization relationship. Where you decide that a generalization relationship exists, make a sketch of the generalization relationship in either of the styles shown in Figure 5. Your sketch should include a name for each class and should indicate which of the classes, if any, are abstract. Suggest a set of attributes for each class involved in the generalization relationship. A department store has a number of departments, each of which is headed by a manager, whose salary depends on their grade. Sales assistants are assigned to a particular department. For security purposes, each sales assistant is provided with a personal code, which they need to enter into the till when they make a sale. Department managers do not conduct sales transactions, though they sometimes advise customers on products. All staff, including department managers and sales assistants, have unique employee numbers. A car hire firm rents out cars and vans. The firm identifies the vehicles in its fleet by their registration numbers. Customers book rental vehicles via the company's website. When booking a car, the customer needs to select a type of car, e.g., family saloon or luxury model, whereas when booking a van the customer needs to specify the load carrying capacity, gram, 800 kilograms or 1.5 tons. CA University records details of all its lecturers and students, including their postal and email addresses. All lecturers must teach at least one module each year, and may not teach more than 4. Students may choose to study up to 6 modules each year. Discussion. Here is our diagram. Figure 7. Generalization relationship representing staff in the department store. Figure 7 indicates a generalization relationship with staff member as the parent class, and department manager and sales assistant as its child classes. The final sentence in the extract implies that there are more categories of staff than just department managers and sales assistants. We do not know anything about these categories other than that they have an employee number attribute, but it is reasonable to assume that they have some significance in the system domain. From the information provided, they can be modeled by the staff member class, which should therefore be a concrete class. Suitable attributes for the three classes would be, for staff member, employee number for department manager, grade, salary for sales assistant, code. Here is our diagram. Figure 8, generalization relationship representing vehicles in the car hire firm. This description indicates a generalization relationship with vehicle as the parent class, and car and van as child classes. The extract implies that all vehicles in the fleet are either cars or vans, so vehicle can be designated as an abstract class. Suitable attributes are as follows. For vehicle, registration number. For car, type. For van, capacity. See, conceptually, there is no generalization relationship between student and lecturer. A student is not a kind of lecturer, nor is a lecturer a kind of student. The attributes of lecturers and students, as described in the extract, are identical, and both have a relationship with modules, though this relationship is not the same in each case. Lecturers teach modules and students study them. However, the key point is that, conceptually, one class is not a generalization of the other. Students and lecturers do have some things in common, and this might have led you to introduce a parent class for student and lecture classes, called something like university member. The reason why we consider this to be an inappropriate model at this stage is explained below. In the hospital system, we noted that both junior doctor and consultant doctor are subclasses of the abstract class doctor. Since doctor is an abstract class, it will not have any instances, so it might be thought that we could do without a doctor class. The key reason why it should be retained is that it models a significant category of entities in the system domain. The requirements document has significant things to say about doctors in general. For example, each doctor is in exactly one team, and a patient may be treated by any number of doctors, but they must all be in the team that cares for the patient. A doctor can treat any number of patients. As the aim is to model the system domain as closely as possible, it is entirely appropriate that a doctor class should be included. In contrast, the description of aspects of a university in Activity 6C above says nothing about members of the university, a category which would include students and lecturers. So although students and lecturers have some shared attributes, there is no evidence to indicate that a grouping of these two categories is of significance to the system domain, and therefore no good reason for including a university member class as a parent class of student and lecturer. As a further example, consider the system for booking badminton and squash courts described in self-assessment question 1 at the end of subsection 2. 3. Here is part of the system description. A computer system is required for booking badminton and squash courts in a sports center. Suppose that classes identified as necessary for modeling the system domain include squash court, badminton court, booking and member. Although only badminton courts and squash courts are explicitly referred to, these two entities are clearly kinds of court, and the description indicates that they have a shared significance in the system domain, the fact that they are bookable. It could therefore be appropriate to include an abstract parent class, court. 3. 6. Class or attribute. In determining suitable classes and attributes for the hospital system, this section has presented a number of guidelines and techniques as if applying these were a fairly straightforward process. Conduct a textual analysis. Apply the rejection guidelines. Complement this by considering categories of likely classes. Identify the attributes. Identify any generalization relationships. In practice, arriving at a set of appropriate classes and attributes is rarely so straightforward. Rather than working with a short, relatively simple description, you may find that a requirements document describes a system domain with much greater complexity of detail and meaning. One issue that arises time and time again is whether something is an entity or the property of an entity. Should it be modeled as a class or an attribute? This difficulty can be illustrated with reference to a couple of examples. Suppose that during the requirements specification phase you had asked the chief physician what sort of detail is needed about doctors, and that she had replied, as well as a name, a doctor has a title. Also, a record is kept of the institution where he or she qualified. It seems fairly obvious that title is just another attribute of doctor, but how would you model the reference to institution? Would you introduce an institution class, or would it be sufficient, for example, to add an institution name attribute to the doctor class? This depends on what sort of information about institutions needs to be recorded. You would need to question the chief physician further. Suppose that in response to further questioning she added, I need to know how many of my junior doctors qualified at a particular institution, and the name of the chief physician at that institution. This indicates that institution is significant in its own right. It has properties and will need to be included as a class in the model. On the other hand, her reply might have been, just the name of the institution will do. That will enable me to research any further details. In this case, an institution name attribute in doctor would be all that was needed. Now let's revisit the vehicle hire example in Activity 6b. The description contains the following statement. When booking a car, the customer needs to select a type of car, e.g., family saloon or luxury model. From this information alone, it was reasonable to model type as an attribute of car, but what you know about car hire might lead you to question whether the type of car might have a significance in its own right. Wouldn't the system need to record the properties of each type of car, such as its number of seats or hire cost? If so, then type of car might be a valid conceptual class. As an analyst, you would need to question the client further about this. One of the strengths of an object-oriented development approach such as the one adopted in this unit is that the activity of building a conceptual model forces the developer to examine the meaning of statements about the system domain. This iterative questioning is also indicative of a good analytical approach in general, an active exploration of meaning rather than a passive acceptance of requirements. Having identified an initial set of classes and attributes for the hospital system, and which of these classes might be generalizations of others, or abstract, it is now possible to move on and consider the associations between the classes. However, it is important to bear in mind that the process of developing a conceptual model is an iterative one, and that the set of conceptual classes is still provisional. It may be that the analysis of the associations between classes will require them to be revised. Associations. 4. 1. What is an association? In the previous section you learned how to identify conceptual classes and their attributes from a requirements document. In this section you will review what is meant by an association. Learn how to identify associations. Just as a class can be thought of as a set of objects that have common attributes and behavior, so an association between two classes is a set of links that have a common meaning. You have seen that a link is a connection between a pair of objects, one from each class, that is significant for the system domain. For example, in the DVD library system, each film object may be linked to a number of DVD objects, with each link between a single film object and a single DVD object representing a connection between a film and a DVD. The situation at a particular point in time can be illustrated by an object diagram, such as the one in Figure 9. Figure 9. Object diagram illustrating links between film and DVD objects. The links in Figure 9 each model the fact that the particular object at one end of the link represents a DVD, which is a copy of the film represented by the film object at the other end. So these links are said to be instances of an association that we might call as copy, which exists between the classes film and DVD. As with classes and attributes, the name given to an association should be a single word and should give an indication of the meaning of the association. The usual convention is for association names to start with a lowercase letter. Note that the name of an association does not imply anything about its direction. This means that naming the above association meaning a film is copied by a DVD would have been just as valid as naming it meaning a DVD is a copy of a film. 4. 2. Identifying associations. In practice, the identification of associations often proceeds in parallel with the identification of classes. When you are considering a possible class, it is also natural to think about the connections that the entities it represents might have with other entities in the system domain. However, as with classes, textual analysis can also help to identify associations. Just as nouns and noun phrases can suggest candidate classes, so the grammatical structures that connect these nouns and noun phrases in the text of a requirements document can suggest likely associations. As an example, here again is the requirements document for the DVD library system. We have started our search for suitable associations by first highlighting the nouns and noun phrases that correspond to the conceptual classes which have already been identified by showing them in bold italic font, and we have then underlined any grammatical structures that connect these classes. System domain. The DVD library holds DVDs of a number of films. It may have any number of copies of each film. The system should, for each film, hold the film's title. No two films have the same title. A library member can borrow any DVD of a film that is not currently on loan. However, no member can have more than 6 DVDs on loan at once. A borrowed DVD must be returned within 3 days. When a library member returns a DVD, it immediately becomes available for loan to other members. Each DVD has a unique identifying number. Each member of the library has a unique membership number. The system also holds each member's name. Use cases. The DVD library system will provide support to the library by enabling the library staff to do the following. A. Get number available. The staff member identifies the film. The system displays the number of copies available. B. List films. The staff member identifies the member. The system displays a list of the film titles and return dates for each DVD that the member has on loan. C. Borrow DVD. The staff member identifies the DVD and the member who is borrowing it. The system records the fact that this copy of the film is no longer available for loan, that it is on loan to the member identified, and the date on which it was borrowed. D. Return DVD. The staff member identifies the DVD. The system records the fact that this copy of the film is now available for loan and that it is no longer on loan to the member who returned it. Concentrating on the nouns which represent classes allows us to disregard relationships that involve other aspects of the system, such as attributes, general behavior and user interface, or entities outside the scope of the system. Here are some examples of the sorts of thing that can be ruled out. Relationships involving classes and their attributes, e.g. Films have title. Relationships describing the behavior of the system, e.g. System displays number of copies. Relationships involving entities outside the scope of the system, e.g. Library holds DVDs, staff member identifies member. Remembering that copy is a synonym for DVD, underline phrases such as DVDs of a number of films, copies of each film. Suggest an association between and representing the fact that a DVD is a copy of a film. The situation involving members, DVDs and loans is a little more complicated. Here are some of the relevant phrases. Library member can borrow DVD. Library member returns DVD. Copy is on loan to the member. These might initially appear to indicate an association between and as in the following class diagram. Figure 10. Possible association between and. However, the dates on which a loan or borrowing is issued and is due for return also need to be modeled, and in this unit associations do not have attributes. This is why we decided to introduce a class. Returning to the phrases above Figure 10, you can see that both members and DVDs copies are associated with loans. A loan is to a member and consists of a DVD. So we need 2 additional associations, giving us 3 in all, between and between and between and. These associations are illustrated in the class diagram in Figure 11. Figure 11, preliminary class diagram for the DVD library system. The phrases linking entities which correspond to the classes often do more than just suggest the existence of an association. For example, phrases like no member can have more than 6 DVDs on loan at once give us information about the number of links that are possible between an object of one class and objects of an associated class at any given time. We will return to this in the next subsection. The next activity asks you to apply your new skills of identifying associations to the hospital system. The requirements document for the hospital system is set out in the PDF document below. You will need to refer to this in order to complete Activity 7. Activity 7. Conduct a textual analysis of the requirements document for the hospital system and draw up a list of possible associations. Remember that you are only looking for likely associations that involve the conceptual classes that have been identified. And you might want to refer back to Self-Assessment Question 2, which is subsection 3. 4, where several of the required associations have already been identified. Discussion. Our list of associations is as follows. In each case we have added, in parentheses, a quote from the requirements document which supports the need for this association. Between and wards, each of which may have on it one or more patients. Between and doctors are organized into teams. Between and each team is headed by a consultant doctor. Between and patient is under the care of team. Between and consultant is responsible for patient. Between and a patient may be treated by doctors. The accompanying phrases indicate that all these associations appear to represent significant connections between entities in the system domain. But as with other aspects of the analysis process, identifying associations is not an exact science, so do not worry if your list was not the same as ours. At the very least, some of the names you have chosen will probably differ, though they should still be meaningful. It is now possible to produce a class diagram, figure 12, showing the set of classes and associations identified for modeling the hospital system requirements. The diagram is not yet complete, as it still requires some additional items of information. Figure 12, an incomplete class diagram for the hospital system associations and generalization relationships. Before moving on, it is worth considering briefly the implications of generalization relationships for associations. As with attributes, any associations involving a parent class will be inherited by its child class S. Figure 12 shows two associations involving connecting it to and connecting it to. The meaning of these associations is that any doctor, whether a junior doctor or a consultant doctor, may be linked to a team or to patients or both. Notice that by including the class, the structure is simplified. If were omitted, would need to be replaced by two associations, one between and the other between and. There would be similar duplication of the association. Because inherits an association with from its parent class, there are two different associations between and. This is fine, but it does have some implications for the consistency of the model, in that a team must contain the consultant doctor that heads it. We will return to this later in the unit. 3. Multiplicity. When discussing the associations for the DVD library system, we noted that a requirements document frequently provides information about the number of links that are possible between objects of particular classes. For example, the requirement stated that no can have more than 6 DVDs on loan at once. For the sake of simplicity, we will assume that a loan involves a single DVD. Therefore, in terms of the model, this means that no object may have links to more than 6 objects at any one time, though it may have fewer such links. To illustrate this, the object diagram in Figure 13 represents a situation where there are 3 members of the library. At the point in time depicted in the diagram, has 3 DVDs on loan, has no current loans, and has 1 DVD on loan. Figure 13, object diagram showing as tone is of links. The number of instances of a class that can be linked by a particular association to a single instance of the class at the other end of the association is known as the multiplicity of the association at the end. For example, suppose that each student on a particular course must have a single tutor, and that each tutor must be assigned to 20 students. The multiplicities of association between the classes and would be shown as in Figure 14. Figure 14, multiplicities for association between and. Figure 14 tells us that each object must be linked to exactly one object and that each object must be linked to 20 objects. The multiplicity may be a single figure or a range. For example, a member of the DVD library may, at any point in time, have any number of loans between 0 and 6. That is, the multiplicity of the association at the end is 0 to 6 and would be indicated on the class diagram by writing on the association next to the class. Although a member may have a number of loans at a particular time, each loan will be linked to only a single member, so the multiplicity of at the end is sometimes expressed as exactly 1. Figure 15 shows the class diagram for the DVD library system with the multiplicities for added. Figure 15. Class diagram for the DVD library system showing multiplicities for the association. Now consider the association. A particular object will always be linked to a single object. The multiplicity of is therefore at the end. However, a DVD may or may not be on loan, so a particular object is linked to 0 or 1 objects and the multiplicity of at the end is therefore described as 0 or 1. Self-assessment question 3. What is the multiplicity of the association at the end? Answer. A particular DVD is a copy of a single film, so the multiplicity at the end of is. What about the end of? The requirements state that the library may have any number of copies of each film. In other words, there may be no copies at all, but there is no upper limit. Such a multiplicity is expressed as described as 0 or more, where indicates that there are no upper restrictions on the number. Figure 16 shows the class diagram for the system with all the multiplicities added. In this context, the is usually referred to as star. Figure 16. Class diagram for the DVD library system, showing multiplicities for all associations. Multiplicity ranges do not need to start with 0. A statement such as members of a book club must choose at least 2 books from the titles on offer each quarter, but may purchase up to 6 books at the offer price would give rise to a multiplicity of described as 2 to 6 at the end of the association between the classes and multiplicities are always written with the smaller number in the range first. Self-assessment question 4. Use figure 17 below to answer the following questions. A. How many courses can a student take? B. How many tutors teach each course? C. How many students can enroll for a course? D. How many courses can each tutor teach? Figure 17. Class diagram representing students, courses and tutors. Answer. A. Between 1 and 4, inclusive i.e. 1, 2, 3 or 4. B. Exactly 1. C. 0 or more i.e. any number. D. Between 1 and 3, inclusive i.e. 1, 2 or 3. The multiplicities of an association answer important questions about the relationship between the two classes involved. The answers to these questions will play a significant part in later phases of the software development process. Questions which are of particular relevance in this respect are: must an instance of one class be linked to at least one instance of the class at the other end of the association, or is it possible that, at a certain point in time, no such links exist? For example, every object in the DVD library system must be linked to an object a multiplicity of 1, whereas an object may or may not be linked to any object at a particular point in time a multiplicity of. May an instance of one class be linked to more than one instance of the class at the other end of the association? For example, an object is always linked to a single object a multiplicity of 1 at any one time, whereas an object may be linked to 0, 1 or more objects a multiplicity of. Is there an upper limit to the number of possible links that may exist from an object of one class to objects of the class at the other end of the association? For example, an object may have at most 6 links to objects. Self-assessment question 5. Using figure 17 for reference, describe in words the multiplicities at each end of the end associations. Answer. Has a multiplicity of 0 or more at the end and 1 to 4 at the end. Has a multiplicity of 1 to 3 at the end and 1 or exactly 1 at the end. Multiplicities for the hospital system. Consider first the association between and. Here are some extracts from the requirements document. A patient may be treated by any number of doctors. A doctor can treat any number of patients. The first extract indicates that there is no upper limit on the number of doctors who have treated a patient. It is also possible that a patient has not been treated by any doctors. They may only just have been admitted to the hospital. For example, so the multiplicity of at the end is. The second extract states that a doctor can treat any number of patients, allowing for the situation where a doctor has not yet treated any patients. The multiplicity at the end is also. Now consider the association between and. Here are some extracts from the requirements document. In the hospital, there are a number of wards, each of which may be empty or have on it one or more patients. Each patient is on a single ward. The first extract states that a single object may be linked to 0, 1 or more objects, indicating a multiplicity of at the end of the association. The second says that each patient is on one ward. Thus each object is linked to exactly one object. The multiplicity of at the end is therefore 1. The class diagram in Figure 18 shows the multiplicities for the end associations. Figure 18, multiplicities for the end associations. You may have wondered why the multiplicities for do not take account of the statement every ward has a fixed capacity, which is the maximum number of patients that can be on it at any one time, so that in practice no ward can have the unlimited number of patients indicated by a multiplicity of. This is because an association represents all the links that are its instances. Different wards have different capacities, so it would not be possible for the multiplicity at the end of the association to specify an upper limit that would apply to all objects. If the requirements had stated, for example, that all wards have a capacity of 15, we could have dispensed with the attribute in and modeled the limit by a multiplicity of at the end of. In general, if you do not know the upper limit for a multiplicity, then the best you can do is assign an upper limit of. In practice, this is likely to indicate an unknown and possibly variable upper limit rather than an infinite one. Activity 8. Make a sketch of the diagram in Figure 18 and add the multiplicities for the associations, and you will need to refer to the requirements document for the hospital system. Click on the View Document link below. Discussion. Figure 19 shows our class diagram. Figure 19, class diagram for the hospital system, showing multiplicities. Here is a brief justification of our solution, including relevant extracts from the requirements document. Each team is headed by a consultant doctor who is in the team. Each doctor is in exactly one team. Remember that consultant doctors are a kind of doctor, so that it is possible to deduce from the second extract that each consultant doctor is in exactly one team. Because the first extract specifies that a team must be headed by a consultant doctor who is in that team, it can also be deduced that each consultant doctor can only head one team. Each team is headed by a consultant doctor in the team. The rest of the team are all junior doctors, at least one of whom must be at grade 1. Each doctor is in exactly one team. The first two extracts indicates that each team must contain at least 2 doctors, the consultant doctor that heads it, and at least 1 junior doctor at grade 1, so at least 2 in all. The third extract provides the multiplicity at the end. Each patient is under the care of a single team of doctors. This tells us that each object will be linked to exactly one object. There is no information on the number of patients that can be cared for by a team, so we use for the upper limit at the end. Since there is no information to the contrary, we assume that it is also possible that there are times when a team has no patients under its care, for example when a team is newly constituted, or when all the patients under its care have been discharged. The consultant who heads that team is responsible for the patient. This is similar to the association. Each patient is the responsibility of a single consultant doctor, and each consultant doctor may have responsibility for 0, 1 or more patients. Activity 9. Suppose that a particular patient, represented as the object called, has been treated by a particular doctor on 3 different occasions. In an object diagram modeling the system domain at some point after these 3 treatments have taken place, how many links would be needed between and? May be an object, or it may be an object. The actual class is irrelevant here. Any kind of doctor may be involved in treating a patient. Discussion. There would be only one link. Although a single object can be linked to 0 or more objects, there can, for a particular association, only ever be a single link between 2 particular objects. As far as the conceptual model is concerned, either a particular doctor has treated a particular patient or not. Multiple treatments are not recorded. We will return to this in the next section. A multiplicity specifies the number of different instances of a class that can be linked to a single instance of an associated class, not the number of links between particular instances of two classes. However, it is possible to have two or more associations between two classes, as in the case of and between and. This might result in there being two links between two objects. In this section you have learned various techniques for identifying associations between classes, which represent the links between the objects of these classes. You also learned about the important role of multiplicities, and how to identify and specify them. Modeling events. 5. 1 criteria for modeling events. In the discussion of classes earlier in the unit, we gave events as one category of thing that could be modeled by classes. You saw an example of this in the DVD library system, where the loan of a DVD by a library member was modeled as a loan class connected to both the and the classes by associations. You have also seen examples where an event is modeled by an association. For example, we chose to model the treatment of a patient by a doctor in the hospital system as an association between the and classes. In this section, you will discover some criteria for deciding whether an event should be modeled as a class or as an association. Self-assessment question 6. Why did we choose to model the loan of a DVD as a class, but the treatment of a patient as an association? Answer. In the case of a loan event, there were requirements for additional information to be associated with each loan. The date on which the loan was made, and the return date. By modeling loan as a class, we were able to model these additional requirements by including appropriate attributes. In the case of the treatment of a patient, there was no requirement to record or provide any information specific to a treatment, other than the patient and doctor involved. If details of each treatment had been needed, then the class would have been a better choice. The object diagrams in Figure 20, below, illustrate the examples that were the subject of SAC 7. Figure 20, object diagrams representing loans and treatments. Figure 20 shows that is on loan to. If, at some future date, borrowed again, the loan involving these two objects would be recorded by a different object, say. Figure 20b shows only that has treated. We know nothing about that treatment, or indeed whether the doctor has treated the patient more than once. In the solution to Activity 9 in the previous section, we said that it was not possible, with our chosen model, to record multiple treatments of a particular patient, say, by a particular doctor, say. If we needed to do this, we would have chosen to model the treatment of a patient by a doctor as a class, each object of which would be linked to an object and an object. A class diagram and an object diagram for this possibility, showing the treatments of by, are given in Figure 21. Figure 21. Modeling the treatments of a patient by a doctor with a class. The class diagram Figure 21 shows that a doctor may provide any number of treatments, and that a patient may receive any number of treatments, but that each treatment involves exactly one doctor and one patient. The class might have attributes to record information such as the date and nature of the treatment, or it might not. The object diagram Figure 21b shows that this model allows for multiple objects, each involving and. The two example systems which form the basis of the next two exercises demonstrate circumstances in which events that do not have properties of their own are nevertheless modeled as classes. But before discussing these circumstances, we would like you to familiarize yourselves with the requirements of these two systems by completing their class diagrams. In completing the diagrams you will also reinforce your understanding of some of the ideas introduced in the unit so far. Activity 10. Here is an excerpt from a requirements document for a goat breeding system. A farm needs to record information on the breeding of its goats during the season. The goats are organized into herds, with each goat belonging to a single herd, and a herd containing many goats. There are three sorts of goat. Billy goats males, nanny goats females, and kids which, since they do not mate in the current season, are not considered to be either billy goats or nanny goats. The farm needs to have a record of the mating behavior of each nanny goat and billy goat during a particular season, and of the offspring which result. A Billy Goat mates one or more times during the season, but only with nanny goats that are in its own herd. A nanny goat mates exactly once per season. A mating may produce several offspring, kids or none. All kids remain in the same herd as their parents. The following classes have been identified as appropriate. And notice that the class represents an event involving a nanny goat, a Billy goat, and possibly several kids. Use the above description to identify likely generalization relationships, associations, and multiplicities and draw the class diagram. Discussion. Our class diagram is shown in Figure 22. Figure 22, class diagram for the goat breeding system. You have almost certainly come up with different names for the associations. Incidentally, it's worth noting that there is no reason why you should not use the same name for two different associations. For example, you could have given the association between and the same name as the association between and, say. We have avoided the use of duplicate association names in this unit, as this would make our models more difficult to discuss. We have taken the view that a herd must contain at least two goats to exist. Note that the class is abstract, as there are no goats per se, only Billy goats, nanny goats, and kids. Mating is an example of an event that is modeled by a class. We will return to this shortly. Activity 11. Here is an extract from the requirements for a system used in organizing an open university day school, referred to as the day school system. A region of the Open University needs to maintain information about a day school for M256. The day school consists of a number of sessions. Two types of participant, tutors and students, are involved in these sessions. The system must record the name and email address of each participant. Each session is taken by a single tutor, and each tutor must take at least one session, though some of the tutors will take a number of sessions. Students need to register for each session that they wish to attend. A maximum of 20 students can be catered for in each session. Once this limit is reached, no further students may register for that session. Only students who register for at least one session are recorded by the system. At each session a different booklet of exercises is used. Each booklet is written by a number of the tutors taking part in the day school, one of whom must be the tutor who is taking the session that uses the booklet. The following classes have been identified as appropriate. And use the above description to identify likely generalization relationships, associations, and multiplicities and draw the class diagram. Discussion. Our class diagram is shown in Figure 23. Figure 23, class diagram for the day school system. During the period of organization for the day school, it is possible that no student has yet registered for a particular session. Hence the multiplicity of at the end of. A session is an example of an event modeled by a class. In each of exercises 10 and 11 we chose to model an event as a class in the goat breeding system and in the day school system. But neither of these events has properties that need to be modeled as attributes. Activity 12. Study the class diagrams for the goat breeding and day school systems. Can you identify any similarities in the ways in which the end classes fit into their respective class diagrams? Discussion. And each have associations with three distinct classes. Is associated with, and. Is associated with, and. The two systems you have just explored illustrate a common situation where an event involves three or more types of entity from the system domain. A single mating event in the goat breeding system involves a nanny goat, a Billy goat, and the offspring which result from that mating. In association between any two of the participant classes fails to capture this three-way relationship. In this unit, an event that involves objects from more than two classes will always be modeled by a class, even if there are no properties associated with the event. Contrast this with the modeling of another event in the day school system, a student registration. This involves only two classes and, furthermore, it has no properties of its own that need to be modeled as attributes. Registration is therefore modeled as an association between and. What is really needed here is an association between three classes, but as associations can involve only two classes, an event class is introduced to link all three classes. 5. 2. Summary of criteria. We will end this section by summarizing the criteria to be considered when deciding whether an event is best represented by a class or an association. Does the event have any properties whose values need to be recorded? For example, in the hospital system, had there been a need to record the date of a patient's treatment or the medication that a treatment involved, we would have modeled treatment by a class associated with and. Does the event involve more than two other significant entities? For example, where nurse is part of our system domain, a treatment might sometimes involve a nurse as well as the patient and the doctor. In that case too, a class would be necessary, since three objects would need to be linked rather than just two. Do different occurrences of the event involving the same entities need to be recorded? For example, if there were a need to record each treatment of a given patient by a particular doctor, a class would be appropriate, because an association only allows for one link between the same two objects. Where none of these situations pertains when an event involves instances of only two classes, has no significant properties of its own, and where it is not necessary to record multiple occurrences involving the same two entities, the event should normally be modeled as an association between the two classes. Activity 13. Consider the following excerpt from a requirements document for an election campaign system. Identify all the events in the description that should be represented in the conceptual model. Decide which of them should be modeled by a class and which by an association, and give reasons for your decisions. Sketch a class diagram, excluding multiplicities. A system is required to model the organization of an election campaign by a constituency political party. During the campaign, local activists carry out telephone canvassing and visit local community organizations from which the party hopes to gain support. The party records all the telephone calls and visits that have taken place. In the case of telephone calls, the date of the call is recorded, together with a note of any issues mentioned by the constituent as likely to influence their voting behavior. The party also organizes a number of public meetings in different parts of the constituency. Each of these meetings is chaired by a member of the local committee, and involves at least two speakers, a local activist and a guest speaker selected from a panel drawn up by the national headquarters of the party. You may assume that the following classes have already been identified as necessary. And discussion. The description mentions three relevant types of event: visits to local organizations, public meetings, and telephone conversations. The visits involve only two classes, and there is no indication that specific information needs to be recorded about visits or that their number is significant, so it is appropriate to model them by association between and. Public meetings, on the other hand, involve instances of three other classes, and it is therefore appropriate to model this event as a class. Telephone conversations between party activists and constituents involve only two classes, but we are told that certain details of the conversation, the date on which it took place, and the issues raised by the constituent are recorded. To model this, a class is needed, which will have two attributes, and a class diagram for the system excluding multiplicities is given in Figure 24. Figure 24. Class diagram for the election campaign system excluding multiplicities. Invariants. 6. 1. What is an invariant? The aim in constructing a conceptual model is to capture all the relevant information about the system domain provided in the requirements document so that this model can form the basis for the structure of the system. To complete the process, there is one more component to add. Invariants. In this section, you will learn what is meant by an invariant, how to identify and express invariants. An invariant is any condition on the objects of a conceptual model, their attribute values and links, which must hold for the requirements to be satisfied and the consistency of the model to be guaranteed. Such a condition represents a constraint on the real-world entities modeled, i.e., a constraint on the system domain. We start by illustrating this concept with some examples from the hospital system. You will find it easier to follow this discussion if you have the requirements document and the class diagram for the system in front of you. These can be found in sections 3 and 4 of the PDF document below. Consider the following extracts from the requirements document for the system. Each patient is under the care of a single team of doctors. The patient may be treated by any number of doctors, but they must all be in the team that cares for the patient. These extracts both imply invariants that must be true of our model at all times. Each object must be linked to one object, not zero, not more than one. All the objects linked to an object must be linked to the object to which that object is linked. We can express these two invariants more precisely as follows. Each object is linked to exactly one object. If is any object, then any object linked to is also linked to the object which is linked to. The first of these invariants imposes a condition on the number of links that are allowable between objects of two classes. Fortunately, some invariants, such as those concerned with the numbers of links allowed between an object of one class and object S of an associated class, may be evident from the class diagram, and so they would not normally need to be expressed in words. For example, this first invariant is represented by the multiplicity of 1 at the end of the association. However, other types of invariant cannot be shown using the notation used for class diagrams here, and need to be included in the text which accompanies the diagram. The second invariant above is one such example. It expresses a dependency between links of more than one association. We will shortly discuss invariants which impose other types of condition on objects, attributes and links, but we will first explore the second invariant a bit more closely by considering, in Activity 14, how it imposes conditions on objects and links. Activity 14. Figure 25 shows two object diagrams, each modeling part of the hospital system domain at a particular time. One of the diagrams depicts a combination of objects and links which is invalid with respect to the second invariant above. Which diagram is invalid and why? You may assume that all relevant links are shown. Figure 25. Object diagrams for the hospital system, one of which depicts an invalid combination of objects and links. Discussion. Figure 25a is invalid when an object and in this case the object are linked to each other. Both must be linked to the same object, according to the second invariant above. Now consider the following extract from a requirements document for the hospital system. There are two types of ward, male wards and female wards. A ward can only have patients of the specified sex on it. This constraint can be represented in the conceptual model as the following invariant. The attribute of any object has the same value as the type attribute of the linked object. This invariant expresses a condition on the relationship between attribute values of linked objects. Activity 15. Using the requirements document for the DVD library system given in subsection 3. 2. In its completed class diagram in Figure 16, identify two invariants on the model of the DVD library system. One invariant should relate to the number of allowable links between two objects, and the other to the attribute values of objects of a particular class. Try to express your invariants in terms of objects, attribute values and links, but do not spend too much time getting the wording precise. Discussion. Each object is linked to no more than 6 objects. For each object, the difference between the values of its and attributes is 3 days. The examples above demonstrate that invariants can involve a number of different aspects of the conceptual model. Invariants involving additional types of constraint will become evident as we carry out a detailed analysis of the system domain for the hospital system in subsection 6. 2. And consider the conditions needed to ensure the consistency of that model. First, though, we consider the forms in which invariants are included in the conceptual model. As the model will contribute to the design of the system, and ultimately its implementation, it is important that invariants are expressed clearly and without ambiguity. An invariant should be formulated as a statement that can be tested for its truth. As evidenced by some of the examples already considered, this is not always easy. Furthermore, there is often more than one way of expressing a particular invariant. For example, we could equally well have stated the second invariant in Activity 15 as: the attribute of each object has a value that is 3 days later than that of its attribute. Activity 16. Figure 26 is a fragment from the class diagram for a university system. The class has attributes, and, while the class has attributes, and Write down an invariant which states that the tutor allocated to a student must be from the same region as the student. Figure 26, fragment of class diagram for university system. Discussion. The attribute of each object has the same value as the attribute of the linked object. Or, the attribute of each object has the same value as the region attribute of each object to which that object is linked. Activity 17. Study the requirements document for the DVD library system and see whether you can identify any further constraints on the system domain that require invariants involving just the values of attributes. Discussion. The description sets out several constraints which will give rise to invariants concerned with the uniqueness of attributes. No two members may have the same membership number. No two DVDs may have the same number. No two films may have the same title. We could express the invariants noted in Activity 17 in terms of objects and attribute values. If this were done for the first one, it would read as follows. If there are any two distinct objects, then the value of the attribute of is not the same as the value of the attribute of. Notice that the introduction of identifiers to refer to objects, e.g., and makes it easier to express the invariant clearly. Invariants concerned with the uniqueness of attributes are so common that we will not generally ask you to identify them. However, this does not mean that they are not important. For simplicity, our models will include this information in the comments that accompany attributes in the class descriptions, as we have done for the incident attributes in the hospital system. Activity 18. There is one further invariant for the DVD library system. Study the two object diagrams in Figure 27, which model the situation regarding two particular films at a certain point in time. One of these illustrates a combination of objects and links which is invalid with respect to the attribute of, and the other a valid combination. Attributes for the objects and the objects are not depicted because they are irrelevant in this exercise. Figure 27, object diagrams for the DVD library system, one of which illustrates an invalid combination of objects and links. Identify which is the invalid combination and which is the valid combination. Explaining your answer, you may assume that all relevant links are shown. B. Write down a real-world constraint that requires an invariant to ensure that invalid combinations such as the one you have identified in Part A cannot occur. Discussion. A combination A is invalid. The diagram shows that the library has 3 copies of the film Lord of the Flies, of which 2 are on loan. The number available for loan is therefore 1, but the attribute of the object represented by has the value 2. Combination B is fine, as the value of the attribute is consistent with the number of objects which are linked to the object but not linked to any object. B. The real-world constraint is that the number of copies of a film that are available is the number of DVDs of that film which are not currently on loan. The invariant noted in Activity 18 can be written as: for any object, the value of its attribute is equal to the number of objects it is linked to which are not linked to an object. We will now complete our list of invariants for the hospital system. 6. 2 remaining invariants for the hospital system. Uniqueness of attribute values. There are 2 of these corresponding to the constraints that the team code of each team is unique and that the ward name of each ward is unique. Constraints on the values of particular attributes. The requirements document states: the system displays for each such junior doctor their grade 1, 2 or 3. This constraint could be included in the model as the following invariant: the attribute of each object has a value which is either 1, 2 or 3. Similarly, there are constraints on the sex of patients and the type of ward which must be male or female in both cases. We take the view that invariants involving the uniqueness of attribute values or the allowable values of a single attribute are most simply and clearly expressed in a comment alongside that attribute on the class description, as we have done in the case of the descriptions for the hospital system. In addition to constraints arising from the requirements document, there can be restrictions on attribute values that are just common sense, such as the date of birth of a patient not being later than the current date, or the number of free beds on a ward being non-negative. It is not necessary at this stage to identify such constraints explicitly. Numbers of links between objects. There are a number of invariants shown by the multiplicities of the associations in the class diagram. These do not need to be listed. However, not all conditions on the number of links between objects are evident from the class diagram. As we have discussed, the relationship between teams and the doctors that comprise them has been modeled as a single association between and rather than as two separate associations, one between and one between and. Although the multiplicity at the end of correctly reflects the number of doctors that can be contained in a team, it does not fully reflect the allowable number of junior doctors and consultant doctors in a team. Activity 19. Using the first part of the answer to Activity 15 as a model, write down two invariants, one which imposes a condition on the number of objects that may be linked via to an object, and one which imposes a condition on the number of objects that may be linked to an object. Discussion. Each object is linked via to exactly one object. Each object is linked to at least one object. In the first invariant given in the discussion to Activity 19, notice the inclusion of via to identify the relevant association connecting and. This is because there are two associations between and namely, and it is therefore necessary to be explicit about the particular association being constrained. In other words, if in stating an invariant there is more than one association between two classes involved, it is necessary to specify an association name to clarify which association is being discussed. The statement from the requirements document which gives rise to the two invariants in Activity 19 is as follows. Each team is headed by a consultant doctor who is the only consultant doctor in the team. The rest of the team are all junior doctors, at least one of whom must be at grade 1. It indicates that for both the answers to Activity 19 there is a need for an even tighter condition. The single consultant doctor in the team must be the consultant doctor that heads the team, and at least one of the junior doctors in the team must be at grade 1. The second invariant can be extended to reflect this, as follows. Each object is linked to at least one object for which the attribute has a value of 1. We will return to the first invariant in Activity 21. Relationships between attribute values. We have formulated an invariant reflecting the fact that the sex of a patient must be the same as the type of ward to which they are admitted. See the discussion following Activity 14. We also know that each ward has a maximum capacity. The number of free beds must be consistent with this, leading to the following invariant. For each object, the value of its attribute is less than or equal to the value of its attribute. Activity 20. The invariant we have just discussed constrains the relative values of two attributes of the same object. Write down a real-world constraint that requires a similar invariant involving attributes of another class in the hospital system. Discussion. A patient's age is the difference in years between the current date and their date of birth. The invariant noted in Activity 20 could be formulated as follows. For each object, the value of its attribute is equal to the difference in years between the current date and the value of its attribute. Relationships between attribute values and links. Before Activity 20, we discussed the relationship that needs to be preserved between the capacity of a ward and the number of free beds on that ward. A related factor is the number of patients already on the ward. The invariant should be extended to take account of this, as follows. For each object, the value of its attribute is equal to the value of its attribute minus the number of objects to which it is linked. Relationships between links. You have already seen an invariant involving links of the associations, and connecting the classes, and. A similar invariant arises in connection with the associations, and. The requirements state. Each patient is under the care of a single team of doctors. The consultant who heads that team is responsible for the patient. See the second invariant at the beginning of subsection 6. 1. The relevant fragment of the class diagram is shown in Figure 28. Figure 28, a loop giving rise to an invariant. The diagram represents the facts that a patient is cared for by a single team and is the responsibility of a single consultant, but there is nothing in the diagram to indicate that the consultant who is responsible for the patient must have a team that cares for that patient. This is clearly important, and we need to include it in the text that forms part of our model. Remember that the association names are needed here to avoid ambiguity. We can state the invariant as follows. The object linked to any object via is linked via to the object to which that object is linked. You can see from figure 28 that the three associations involved in this invariant form a loop, as was the case with the invariant involving the and associations at the beginning of subsection 6. 1. Invariants are often but not always required when a number of associations in a class diagram form a loop. Activity 21. In the discussion following Activity 19 we concluded that an invariant was required to reflect the constraint that the consultant doctor in a team must be the consultant that heads the team. Which associations are involved in this invariant? B. Write down the invariant required. Discussion. The associations involved are and. B. The invariant can be written as follows. The object linked to an object via is linked to the same object via. The invariant which was the subject of Activity 21 also involves a loop as shown in Figure 29. However, although there are three classes shown in this diagram and the loop is between only two classes and. This is because inherits the association from since it is a specialization of and consequently is in a loop with via the and associations. Figure 29. The and classes and the associations between them. Activity 22. Look again at the description of the goat breeding system given in Activity 10 and the class diagram given in the discussion of the exercise. Identify and extract from the description which gives rise to one or more invariants that cannot be deduced from the class diagram. B. State the invariant S. Discussion. The invariant S can be identified from the following extracts from the description. A Bibli goat mates several times during the current season but only with many goats that are in the same herd as the Bibli goat. A mating kid produce several offspring, which of course are kids and are in the same herd as their parents. In other words, if a Bibli goat and a nanny goat mate, they and their offspring must be in the same herd. B. Here is a single invariant covering the relationships between all three kinds of goat. All the objects linked to each object are linked to the same object. There are a number of other ways of expressing this invariant. For example, if is any object, then the and objects linked to, and any objects linked to, are linked to the same object. Alternatively, the invariant could be formulated as two separate invariants, each involving two of the associations, and, together with the association. Note that because generalises, and, all their instances are also instances of and so are linked to instances of via. Some of the invariants we have identified above could have been avoided by choosing an alternative way of modeling the system domains concerned. For example, representing the fact that each team of doctors includes both a consultant doctor and a junior doctor could have been achieved by replacing the association between them with two separate associations, one between and one between and. We could even have introduced a separate class for grade 1 junior doctors and connected it with a third association. However, this alternative model would have introduced more complexity into our class diagram and would still have required some invariants, so would not have provided any advantage. It is an understanding of what is significant in the system domain that should inform decisions as to which classes and associations are most appropriate. However, as we have already said, the construction of a conceptual model is not an exact science. The best advice at this stage of the modeling process is to choose the simplest option that accurately reflects the situation in the real-world system domain. Any appropriate changes or improvements to the ensuing model of the system structure can be considered later in the development. Having specified invariants for the hospital system, we include these in the text which, together with the class diagram, constitutes our model. A consolidated set of the invariants for the hospital system is given and can be found in the PDF document below. Activity 23. Consider the day school system described in Activity 11 and the class diagram given in the solution figure 23. Identify an excerpt from the requirements document which gives rise to an invariant. B. State this invariant. Discussion. Each booklet is written by a number of tutors, one of whom must be the tutor who is taking the session that uses the booklet. B. The object linked to any object is linked to the object linked to that object. As usual, there are other, equally correct, ways of expressing this invariant. Activity 24. Consider the election campaign system described in Activity 13. Suppose that the conceptual model for the system contained the following invariant. Each object linked to an object is also linked to two or more objects. Write down the real-world constraint that this invariant would represent. Discussion. A local activist who speaks at a public meeting must have visited at least 2 community groups. In this section, you have learned what is meant by an invariant and how to identify and express them. In the process, a list of the invariants for the hospital system has been drawn up. In the next, short section you will explore some of the implications of invariants for other aspects of the model, derived attributes and associations. 7. 1. Using invariants to derive attributes. In this section, you will learn that some attributes and associations in a conceptual model are derivable from others. How invariants are involved in this process. The need for invariants in a conceptual model arises from the fact that the entities in the system domain may be interdependent in a way that is not evident from their representation in the conceptual model's class diagram and class descriptions. Where there are constraints on some aspect of the system domain, an invariant spells out the conditions that ensure that this constraint is reflected in the model. Some invariants express a relationship between 2 or more elements of the model. For such invariants, it may be possible, given the values of one or more elements, to work out the value of some other element. For example, given the invariant, for each object, the value of its attribute is equal to the difference in years between the current date and the value of its attribute. And knowing both the current date and the value of an object's attribute, it is possible to work out the value of the object's attribute. You might justifiably ask why the class needs both the attributes and. The simple answer is that they are both explicitly mentioned in the requirements document. However, in our final system it may not be necessary to implement both these attributes as instance variables. This is not a decision that can be made until the analysis process has advanced beyond the conceptual model. It will depend on the results of a detailed analysis of the behavior of the system, which is yet to be carried out. This analysis may reveal that one or other of the attributes does not need to be implemented explicitly, or it may be that the context in which each is required indicates the need to retain both. The decision may also depend on other implementation issues, such as whether the implementation language and hardware contain facilities for accessing the current date in a suitable form. At this stage of the development process, the model needs to reflect all the aspects of the system domain implied by the requirements document. This document refers to both the age and the date of birth of patients, so both these properties need to be modeled as attributes of the class. However, it is also necessary to look out for situations where one aspect of the model can be deduced from another and to flag this up as part of our model. An attribute whose value can be deduced from other element S of the model is known as a derived attribute. Derived attributes are indicated in the UML by preceding their names with a slash. So we modified the entry for the class in the class descriptions given at the end of subsection 3. 3 as follows. Class. A patient in the hospital. Attributes. The name of the patient. The sex M or F of the patient. The date of birth of the patient. The age of the patient in years. Activity 25. Identify a derived attribute for the DVD library system and provide a class description for the class to which this attribute belongs. Discussion. In the class can be derived from on the basis of the invariant discussed in Activity 15, which stated that the difference between these two attributes must be 3 days. The class description is as follows. Class. The loan of a DVD. Attributes. The date of issue of the loan. The date by which the loaned DVD must be returned. Alternatively, could be derived from. But note that it would not be possible to derive a patient's date of birth from their age in years. Another attribute value that can be deduced from other aspects of the information in the hospital system is the number of free beds on a ward. In the discussion following Activity 20, we formulated the following invariant, which expresses how the number of free beds on a ward can be derived from other aspects of the model. For each object, the value of its attribute is equal to the value of its attribute minus the number of objects to which it is linked. From this invariant we see that the value of an object's attribute can be calculated from the value of that object's attribute and the number of links the object has to objects. So the attribute should be marked as derived. The attribute of should also be marked as derived, since it can be obtained from the type male or female of the object is linked to. This derivation may seem counterintuitive. It does not seem sensible to work out the sex of a patient from the type of the ward they are on. Nonetheless, it is conceptually possible, so it should be noted. Activity 26. Is the attribute of the class in the DVD library system derived? If so, how? Discussion. Yes, the attribute is derived. It can be calculated from the following invariant. For any object, the value of its attribute is equal to the number of objects it is linked to which are not linked to an object. Activity 27. Consider the following invariant for the DVD library system which is actually captured in the comment on the attribute of the class. If there are any two distinct objects, then the value of the attribute of is not the same as the value of the number attribute of. Does this invariant indicate that any attribute of the class can be derived? Discussion. No. Given the value of the attribute for one object, this invariant specifies what the value of any other object may not be, not what it is. Invariants involving attributes are not always an indication of derived attributes. It depends on the nature of the condition specified. You have seen that where an invariant involves the values of attributes, the value of one of those attributes may be derivable from values of other attributes S and or link S involved in the invariant. However, it is not necessarily the case that it is the invariant that leads you to identify the derived attribute. It could be that you recognize that an attribute can be derived before you consider invariance, or that you identify both aspects of the model in parallel. The important point is to be aware of the relationship between them. Where you have a derived attribute, you will also have an invariant. However, the reverse is not necessarily the case. As you saw in Activity 27 above, an invariant involving attributes does not necessarily indicate that it is possible to derive one of those attributes. 7. 2. Using invariants to derive associations. Just as there is a relationship between invariants involving attributes and derived attributes, so it is the case that invariants involving links of different associations may indicate that one of those associations can be derived from the others involved in the invariant. To explore the sorts of interrelationship that can occur between associations, we will start by revisiting the invariant which constrains the allowable links between the classes, and here is the invariant which was formulated in a previous section. The object linked to any object via is linked via to the object to which that object is linked. This invariant involves the associations, and, as shown in Figure 30, extract from the hospital system class diagram. Now consider the case of a particular object, say, linked via the association to an object, say, which represents the team that cares for the patient. Will in turn be linked via to an object, say, which represents the consultant doctor who heads that team. What the invariant expresses is that the particular object to which must be linked via must be, as shown in the object diagram in Figure 31. Figure 31, links between, and objects. A situation similar to that depicted in Figure 31 holds for all objects. Given any object representing a particular patient, it is always possible to identify the object representing the team which cares for the patient by traversing the link, and then the object representing the consultant doctor who heads that team by traversing the link. As this must be the consultant doctor who is responsible for the patient, it is therefore possible to infer, for any object, the particular object representing the consultant doctor who is responsible for the patient, i.e., the link between the object and the object. In other words, it is possible to derive from and. The association is called a derived association. As with a derived attribute, the name of a derived association in a class diagram is preceded by a slash. As illustrated in Figure 32. Figure 32, a derived association. As with derived attributes, you might wonder why the derived association is not simply removed. It is, in a sense, redundant. There are two reasons. The first is that models a relationship that is explicitly mentioned in the requirements document, the responsibility of consultant doctors for patients. It is important, at least at this stage of the development process, that this relationship is explicitly modeled. The second reason for retaining is that its designation as a derived association is somewhat arbitrary. Consider the following invariant involving and, which is equivalent to the one above. The object linked to a given object is linked via to the object to which that object is linked via. Working from this version of the invariant, we could equally well have said that the association could be derived from the and associations, and that it was therefore that was redundant rather than. It is only when the detailed behaviors of the system are analyzed in subsequent stages of the development process that we can decide which, if any, of the associations related in this way is actually redundant. However, it is important that the class diagram in the conceptual model should indicate any derived associations that we have identified. For an association to be derivable, all the links of the association must be derivable. With this in mind, can the association be derived from the associations and? We will answer this question in terms of the multiplicities of the associations involved. It will help to refer to figures 31 and 32. Suppose an object such as in figure 31 is linked to an object. Then the object linked to via must also be linked via to. In other words, if there is an object linked to an object, then it is possible to derive the link between the object and the object. Consider, however, the situation depicted in figure 33. A consultant doctor represented by heads a team represented by. Suppose also that this particular team does not yet have any patients under its care. This is entirely possible, as indicated by the multiplicity of at the end of. In this case, the consultant represented by would not be responsible for any patients. Figure 33, the object which is not linked to any objects. We could equally have traversed the links the other way and said, locate first the object linked to and then the object linked to that object. To derive the link between and shown in figure 33, it would be necessary to locate first the object linked to via the association and then the object linked to that object via. Neither of these links exists. Therefore, it is not possible to derive the link shown in figure 33. In summary, we have shown that the link between and in figure 31 could be derived from the other links in the diagram, but that the link between and in figure 33 could not because there are no other links from which it can be derived. We therefore conclude that because it is not possible to derive all the links of the association, cannot be derived from and. Reviewing this example, it is instructive to note that what we did to show that is not derivable was to consider a possible combination of objects and links, which conform to our model, but where a link could not be deduced from other information. This is a generally useful approach, as you will see in the next exercise. Activity 28. Study the invariant involving the three associations, and given below and the associated extract from the class diagram shown in figure 34. Decide whether the association can be derived from the other two associations, giving an explanation for your answer. If is any object, then any object linked to is also linked to the object which is linked to. Figure 34. The associations, and. Discussion. The association cannot be derived. The hypothetical situation portrayed in Figure 35 will demonstrate why. Figure 35, links between, and objects. Figure 35 depicts the situation where, at some point in time, the patient represented by is cared for by the team represented by, and has been treated by one of the doctors in that team, represented by. The situation is perfectly acceptable within the conditions imposed on the model. The task is to decide whether, given the links from to and to, it is possible to derive the link between and. Having traversed the link from to, you could traverse the links to identify all the objects linked to, that is, all the objects that are eligible to treat. However, it is not possible to deduce that has treated and that has not. In summary, an object linked to an object that is linked to an object is not necessarily linked to that object. Now consider whether it is possible to derive the association from and. Given an object, if there are objects linked to the object, that is, if there are patients cared for by the team represented by the object, then these objects can be identified by traversing the relevant links, while any objects corresponding to doctors who treated these patients can be identified by traversing the relevant links. These objects must be linked to objects via. However, objects corresponding to doctors in the team who have not treated any patients cannot be identified in this way. Consequently, although some of the links are deducible, not all are, and therefore the association is not derivable from AND. Similarly, the association cannot be derived from AND. What the above discussion has shown is that an invariant involving a loop indicates that it may be rather than will be possible to derive one of the associations which make up the loop. Note that a loop may consist of more than 3 classes and associations. In this section, you have learned what is meant by derived attributes and associations, how invariants are used in the derivations, and how they are denoted in the conceptual model. This completes the task of conceptual modeling, and in the next section, all the parts will be drawn together. Conceptual models. 8. 1 conceptual model for the hospital system. We are now in a position to produce a conceptual model for the hospital system. In this unit, a conceptual model comprises the following. A class diagram showing the classes that have been identified as appropriate, any generalization relationships between the classes, any abstract classes, the associations between the classes together with their multiplicities, any derived associations, associated text comprising, for each class, a class description listing the attributes, together with the identification of any derived attributes, and brief comments indicating the purpose of the class and of each attribute. If the class is abstract, any generalization, specialization relationships, any restrictions on attribute values where relevant, including uniqueness constraints, any invariance not evident from the class diagram or class descriptions. In producing the conceptual model, we have aimed to create an appropriate representation of the system domain. However, we have had to make a number of decisions, for example, about which attributes and associations to label as derived. If we had made different decisions, we would have produced a slightly different model, but one which might have been equally good at this stage. There is no one correct model except perhaps in extremely trivial cases, and there are many debates, even among experts, about whether one model is better than another. Our concern is only that you should understand the concepts well enough to be able to produce a reasonable conceptual model. All the aspects of the conceptual model for the hospital system have now been considered. However, before presenting this conceptual model, recall the earlier discussion about the role of the conceptual model in forming a starting point for constructing the system. The conceptual model represents the system domain, the part of the real world relevant to the system. Since a key object-oriented principle is that software objects can usefully mirror real-world entities, the structure set out in the conceptual model is a sensible starting point for the structure of the system. Thus the conceptual model, given below, can be taken as the initial structural model, an initial representation of the software. That is, we will initially view the hospital system as having classes such as AND, whose instances and the links between them represent real-world entities, patients and doctors, etc., and the connections between them are subject to invariance, just as their real-world equivalents are subject to real-world constraints. Here is the complete model, which is also set out in section 4 of the PDF document below, under the heading Hospital System Initial Structural Model. Class Diagram. Figure 36, Class Diagram for the Hospital System. Class Descriptions. Class. A hospital ward. Attributes. The unique name of the ward. Whether the ward is for male or female M or F patients. The maximum number of patients that can be on the ward at any one time. The number of free beds on the ward class. A patient in the hospital. Attributes. The name of the patient. The sex M or F of the patient. The date of birth of the patient. The age of the patient in years class. A team of doctors. Attributes. The unique code of a team class. A doctor at the hospital. Abstract. generalises and attributes. The name of a doctor class. A junior doctor at the hospital. Specialises. Attributes. The grade 1, 2 or 3 of the junior doctor class. A consultant doctor at the hospital. Specialises. Attributes. None. Invariance. The attribute of any object has the same value as the type attribute of the linked object. For each object, the value of its attribute is equal to the difference in years between the current date and the value of its attribute. For each object, the value of its attribute is equal to the value of its attribute minus the number of objects to which it is linked. Each object is linked to at least one object for which the grade attribute has a value of 1. The object linked to an object via is linked to the same object via. The object linked to any object via is linked via to the object to which that object is linked. If is any object, then any object linked to is also linked to the object which is linked to. In order to complete the optional exercise below, you will need to refer to the PDF document attached below. Optional activity. Our analysis of the hospital system has been conducted in a rather artificial manner. We attempted to identify all the classes before identifying their attributes and then the associations between them. Similarly, we did not consider invariance until we had formed the class diagram and class descriptions, and did not identify derived attributes and associations until we had found all the invariants. In practice, you would use your understanding of the system domain to carry out these activities in parallel as you work through the requirements document. Here is a worthwhile activity which you can do now, if you have time. Go back to the requirements document for the hospital system and work through it a sentence or two at a time, building up the class diagram classes, associations and multiplicities and class descriptions as you go, and noting any possible invariants and derived associations when they arise. You may be surprised at how easy it is to get most of the model correct in a short time. The areas requiring most thought are usually invariants and derived associations. Summary. This unit has introduced you to the ideas and techniques involved in forming a conceptual model of a system domain and in particular a conceptual model for the hospital system. Starting with the requirements document for a system, you have worked through the processes necessary to produce the conceptual model. The unit has also introduced some of the UML notation for class and object diagrams. In producing the conceptual model, you have learned how to analyze the requirements document to identify classes and associations appropriate for modeling the system domain, together with their respective attributes and multiplicities. You also learned about the value of generalization relationships in capturing the characteristics common to related classes and how this might lead to the identification of abstract classes. You have seen that objects, attribute values and links may be subject to constraints in the form of invariants, and that attributes and associations can sometimes be derived from other attributes and associations, using invariants. Choices have to be made during this phase of the software development process, and you have seen that there is no one correct conceptual model for a system. Finally, the unit ended by bringing together all the pieces of the hospital system's conceptual model. Glossary. Abstract class. A class which cannot be instantiated, i.e. one which has no instances of its own but only instances of its child classes. An abstract class defines properties which are common to its child classes. It should not be confused with the class representing abstract entities. Abstract entity. An entity that has an existence, but does not correspond to a tangible entity. For example, the film Citizen Kane is an abstract entity, while the DVD which records the film is a tangible entity. Association. An association represents the links that may exist between the objects of two classes. These links have a common meaning and represent a particular relationship connection between these objects that is significant for the system domain. Attribute. An attribute is a property of an object. All objects of a class have the same attributes. Candidate class. A class that may be needed to model a category of real-world entities from the system domain. Child class. A class that is a specialization of some other class, known as its parent class. A subclass. Class in the conceptual model. A A class model is a category of real-world entities from the system domain. Class description. A formal description of a class within a conceptual model or a structural model. Class diagram. Class diagrams are used to show structural aspects of the system domain and of a system at various stages in its development. As a model of the system domain, a class diagram depicts conceptual classes and associations connecting them. As a model of the system, a class diagram depicts the software classes that are involved in the system and the associations connecting them. Conceptual model. The model which represents the significant entities in the system domain and the connections between them as a collection of classes and their attributes, associations and invariants. The conceptual model of the system domain is taken to be the initial structural model for the software system to be developed. It consists of a class diagram, class descriptions and invariants. Concrete class. A class that, unlike an abstract class, may have instances that are not instances of any of its child classes. Constraint on the system domain. A limitation on the entities in the system domain, their properties and relationships. Derived association. An association all of whose links can be derived using other elements of the model. Derived attribute. An attribute all of whose values can be derived using other elements of the model. Event in the system domain. Any significant circumstance, episode, interaction, happening or incident, e.g. deliveries, registrations, bookings, enrollments. Generalization. A relationship between classes that captures the similarities and differences between two related classes. Saying that class is a generalization of class means that the common similar structure and behavior is defined by class A, and the distinctive different structure and behavior is defined by class B. It means that an instance of class B is substitutable for an instance of class A. Inherit. Take on the properties, attributes, and associations of a parent class. Initial structural model. The initial structural model is the conceptual model viewed as the first model of the structure of the proposed software system. In other words, the conceptual and initial structural models look the same but have different perspectives. One models the system domain. The other is taken as the first model of the software system itself. Instance refers to a particular object of a class or a particular link of an association. Invariant. Any condition on the objects of a conceptual model, their attribute values and links that must hold for the requirements to be satisfied and the consistency of the model to be guaranteed. Link. A link exists between two objects when there is a connection between the entities they represent that is significant for the system domain. A link is an instance of an association. Multiplicity. The multiplicity of an association with respect to one of the classes involved defines how many objects of that class may be linked with a single object of the other class involved in the association. Noun phrase. A noun phrase is a sequence of words like number of copies that functions as a noun and which can be used anywhere that a noun could be used. Object in the conceptual model. An object model is a real-world entity from the system domain. Organizational unit. Any part of an organizational structure to which people or things in the system domain belong. Parent class. A class that is a generalization of one or more other classes known as its child classes. A superclass. Role. The particular responsibility or job that a person thing may perform in the system domain. E.g. employee, student, lecturer, driver. Specialization. Saying that a class is a specialization of class means that class A is a generalization of class A. Stereotype. A label providing additional information about some component of a UML model. Stereotypes are enclosed in double chevrons, e.g. abstract. Structural model. A representation of the system in terms of classes and the relationships between them. Subclass. See child class. Substitutable, substitutability. Objects of a class B are substitutable for objects of a class A if anywhere that an instance of class A is required, an instance of class B can be used instead. For class A to be a generalization of class B, instances of B must be substitutable for instances of A. Superclass. See parent class. Tangible entity. A physical thing in the system domain such as an airplane, vehicle, reactor or person, i.e. something that can be seen or touched. Value of an attribute. Specific information that an object holds in respect of an attribute. Do this. Now you have completed this unit, you might like to post a message to the unit forum. Review or add to your learning journal. Rate this unit. Try this. You might also like to find out more about the related Open University course, book a flash meeting to talk live with other learners, create a knowledge map to summarize this topic.